Okay. So watching the animation, we can see that P changes, and as P changes, it affects the curvature of the graph. It changes the end behavior. It changes the increasing and decreasing. It changes the concavity. But one point that the graph will always pass through is 1, specifically 1, 1. And that's more or less going to change. That more or less is not going to change as long as P is the only thing that's changing. When we start to affect the graph with horizontal and vertical shifts, when we start adding and subtracting constants from this, that could change where that 1, 1 value lands, but more or less it's going to stay as is. I did not mean to turn on smart invert. Okay, so to be clear, as my computer proceeds to have a panic attack in the background. P affects the curvature, the end behavior, the concavity, but it doesn't change where 1 is. It changes when it's increasing and decreasing. It does a whole bunch of stuff. Okay. But this is the one question. The first question is the only question that is worth points on today's formative. So let's do this together, because we can kind of classify our p-values into 3 very distinct categories, okay? We can classify our p-values and the behavior resulting from those p-values in 3 very distinct categories. This is the only question that's worth points. So if you guys all could open the formative and do at least this question, you guys will all get credit for today's assignment. Now those patterns are, okay, that we can classify our power functions into 3 categories. Categories where P is greater than 1. Okay, when P is greater than 1. These are the x squareds. These are the x cubes, x to the fifths, x to the fourths. These are our higher order degree functions, okay? And in general, at least in the positive quadrant, these will form some kind of parabola, some parabolic behavior. So in general, if f of x follows that x to the p model and p is greater than 1, it's gonna, in general, kind of look like that pink curve path. It's gonna, in general, kind of look like that pink curve path. The next category is, what if we have a fractional value of p? And when I say a fractional value of p, I'm talking about the fraction itself is less than 1, but greater than 0. Because we can have fractional values of p that are greater than 1. Like we saw them yesterday with the powers of like 3/2 or 4/3 or 5/2, okay? Even those functions, even though we had definite like root behavior in those functions, we still saw a general parabolic curve, a concave up parabolic curve, at least in the positive quadrant. I'm talking about truly when the value of the power is less than 1, but greater than 0. We tend to have these are the square root graphs, the cube root graphs, okay? These are when we have a concave down, kind of sideways parabola looking graph. The graph is still increasing, okay? We still have increasing behavior as x increases. We still have more or less positive end behavior, increasing end behavior. And that follows this red path right here. We can basically classify any power function where p is between 0 or 1 is going to more or less follow this red graph behavior. The last general type of power function that we're going to see is going to be when our p-value is less than 0, okay? When f of x follows that power function rule, but P is less than 0. This is a little bit special because this is what compares it to these are the ones that are more or less the rational functions, okay? Where initially they will be written more likely as x is in the denominator of a fraction, and then the power becomes negative when you bring it up. So it's the 1 over x functions, which can be rewritten as x to like the -1 power. And these more or less are the 3 classifications of our power functions. They all more or less boil down to one of these 3 types of curves. And we're going to look at those 3 types of curves, and we're going to talk about the domain and the range and the concavity and the end behavior of all of these functions today. That's why there's going to be a lot of information today, and why there's really only one checking question, which is this one. So, first of all, we're going to take a minute to look at a couple different versions of these power functions. Okay, I'm gonna actually zoom out so you guys can see all 9 of these graphs at once. And one of the things that we didn't really talk too much about yesterday, because we were focused on the rational functions, and this is really the only thing we're going to talk about the only time we're going to talk about this, is the effect of a constant multiplier or a coefficient leading term. And what I have here is I have 3 different classifications. I have in the first row, we have a linear function, which is technically a power function. I probably should have done it as I probably should have made P between 0 and 1, but whatever. And we have the effects of different k values. We have a negative k value, we have a k value of 1, and we have a positive k value of greater than 1. All right, and I put these in a weird order, but whatever. And what I want you guys to think back to is when we talked about in like your algebra 1 and your algebra 2, is the k value, the constant multiplier or the leading coefficient, is essentially the slope. It's the rate of increase for that function. And basically that's more or less what I want you guys to equate K2. Okay, it's the rate of change for that function. So you'll notice in our linear function, if we have a slope of 1, it's like just increasing steadily. If we have a slope k value of 2, it's increasing more rapidly. If we have a negative k value, it's decreasing. Okay, same thing with our x squared function. If we have a slope of 1, it just acts like it's pure power. If we have a k value of 2, it increases the rate at which our function increases by a factor of 2. And then if we have a negative, it changes all of that increasing behavior to decreasing behavior. And more or less, when we have a negative p-value, this more or less behaves the same way. Okay, it's just a slope function where we have decreasing behavior, and then if we make k negative, it becomes increasing behavior. So to wrap this up, how does the value of k affect the graph? It is essentially more or less the slope, okay? And you've seen this transformation before in terms of the slope of a function when we spent a lot of last year talking about vertex form, and we had that general f of x is equal to a times the function with x minus h plus k, where we saw these in the x squared graphs, we saw these in square root graphs and the cubic graphs, and the whole ah and k thing came up a lot last year. You guys, by the end of it, were sick of hearing me talk about ah and k. That's not going away. And in this case, k is basically equivalent to that a factor, okay, that vertical compression and stretch. Okay. All right. So that vertical compression and stretch. So we're going to look at a few different power functions. We're going to look at power functions where P is greater than 1. We're going to look at power functions where P is between 0 and 1. And we're going to look at power functions where P is less than 0. That was 2. That was question 2. If you guys are following along faithfully with formative, that corresponded to question 2. Okay. So what we're going to look at is we're going to real quick look at our x squared versus our x cubed graph. I don't want to spend a ton of time on this one because this is basically what we talked about for most of topic 1 were the higher degree functions. But let's just real quick review some of our properties. Let's understand our behavior. For our x squared graph, our domain is all real numbers. Our range is restricted. Our y values are greater than or equal to 0. Okay. We have concave up behavior. And for the record, this is all for positive. K values are positive. We have 1 minimum. We do not have any points of inflection. And we have positive end behavior in both directions. For our x cubed graph, our domain is all real, and our range is all real. All right. Domain and our range are both all real. We have a point of inflection, 1 point of inflection. We have, in this case, in the most basic version, we have no minimum or maximum. We have the potential of 2 relative extrema, okay, depending on how complicated the x cubed graph gets. We have both types of concavity. We have half of the graph that is concave up and half of the graph that is concave down. Because we have that point of inflection. We have positive end behavior to the right, and we have negative end behavior to the left. So basically, as x gets bigger, we have positive, and as x gets smaller, we have negative end behavior. Okay. Now, what's interesting is we consider, if like we zoom in on this graph, we consider the fact that both of these functions, if we were just to look at the positive quadrant, okay, if we were just to look at the positive quadrant of these graphs, we can clearly see that both of the graphs are increasing. They are both increasing. As x increases, the outputs are increasing. And at first glance, it totally looks like they are, the cubic graph is definitely increasing faster than the squared graph, which gets really kind of interesting when you actually zoom in really close to some of the behavior of the x cubed graph versus the x squared graph, because we do get some very interesting behavior in values less than 1, because depending on how much you guys remember about how fractions decimals multiply, you guys remember when you multiply something by a decimal, it actually technically gets smaller. So if you're multiplying things by a decimal more often, it's going to get a little smaller but bigger faster. It's a weird little thing. So for the first couple points for values less than 1, our x squared graph actually increases a little bit faster than our x cubed graph before 1. And then once we get to 1, everything kind of like goes off on its own. But in general, regardless of how zoomed in we get, the end behavior remains the same. Okay. we do have moments where we like to zoom in and we like to look at like nitty gritty little parts of it, but at the same time, we also need to be able to zoom out and look at the overall behavior of the graph. And regardless of how nitty gritty the little bits are, if we zoom way out, you can see over here, okay, like at this point, our Y value goes to like 150. The X cubed graph is increasing far more rapidly than the X squared graph because it has an additional factor. And as a result, it's gonna be a much faster rate of increase. But overall, it is still positive end behavior. It is still increasing positive end behavior. So Jaslyn, that's question 3. What do you observe about the end behavior of the graphs, despite the fact that they have remarkably different rates of increase? They are still overall increasing as the inputs increase, the outputs are also increasing. That's the moral of this lesson. Now, we're going to look next at a function that is a little less familiar to you guys, okay? So these are the p-values. These are the p-values that are less than 0 for f of x, where x is raised to the p power. These are p-values that are less than 0. These are the rational functions. So to be clear, y equals x to the negative second. This is the same as 1 over x squared. Y equals x to the negative first. This is the same as 1 over x. Okay. Now, what is really interesting about the rational functions, and we're going to spend an entire topic talking about rational functions. In fact, it's topic 3. So we're going to talk about these in very general terms, and then we're going to spend all of topic 3 talking about these in very specific terms. Looking at these, what's really interesting about the rational functions is because we're dealing with x values in the denominator, you have the possibility of trying to divide by 0. But at this point, we should know you can't really divide by 0 and get a real solution. You technically get infinity. You get like, how many times can 0 go into something? Infinite times, because you can't really divide something 0 times. It's infinite. Which is why when you look at graphs of these, when you look at graphs of rational functions, as the values get closer and closer to, as the input values get closer and closer to 0, you get closer and closer to infinity. Okay, it's the difference about dividing something by 2 versus dividing something by 20 versus dividing something by 200. It's going to get smaller and smaller and smaller. Same thing goes if you're trying to divide it by smaller and smaller numbers. The numbers are going to get very big, very quick, to the point that it approaches infinity. And that creates these things called asymptotes. Bam. So as a result, in general form of power functions, we don't actually have any zeros. For values of p less than 0, we don't really get zeros. I mean, you can sometimes get it if you're adding and subtracting, if you're doing some shifting left or right, up and down, you can get zeros in that behavior, but you're going to have these these undefined values. So in general, for these functions, you're not so much looking for zeros as you're looking for undefined values. Now, at the same time, with the exception of these undefined values, you more or less have I'm trying to figure out the best way to say this. You can basically put all real numbers into these functions, except if the denominator would be 0. Okay, so with the exception of these undefined values, the domain is basically anything except. Okay, so the domain falls into the thing of anything except certain values. And the same thing happens with the range to a certain extent, okay? Because as a result, now at the same time, we think about the fact that if we're dividing, this is the thing that's very hard to wrap your head around at first, unless you kind of really think about it, is you can never get 0 by division. Think about that for a second. If you have something and you're cutting it smaller and smaller and smaller and smaller, you can always cut something to be smaller. You can never cut something to be 0. Okay, because if you think about it in terms of like physics in chemistry, you can always cut a material piece to be smaller, and you can cut it and you can cut it and you can cut it until you're literally slicing separate atoms apart. And even then you can like break the atoms apart because the atoms got smaller parts too. But then we're talking about nuclear chemistry, and like that's a whole different bag. But what I want to impress upon you guys is that you can't get 0 through division. You can't. And as a result, as our input values in these functions get infinitely bigger, our answers are going to get closer and closer and closer to 0, closer and closer and closer to 0, but they're never going to quite equal 0. So this is actually where we introduce a new kind of end behavior. I kind of alluded to this in topic 1, is that we have a third kind of end behavior, because we have usually positive infinity or negative infinity, because it's increasingly forever or it's decreasing forever. But we also have the type of end behavior known as approaching 0. It's approaching 0. It's getting smaller and smaller and smaller, but it's never going to equal 0, but it's approaching 0. So the end behavior for these types of graphs follows that model of our end behavior is approaching 0. So as, I'm gonna leave it red, as x approaches infinity, our y values approach 0 because they're getting smaller and smaller and smaller. And this is true in both directions. So what do we observe about the end behavior of these graphs? They are approaching 0. Now I'm gonna kind of put a big old asterisk. This is gonna be what topic 3 is all about, all right? This is what topic 3 is going to be all about. So we're going to come back to this, and we're going to spend an entire 2 weeks talking about these kind of functions. Okay. We're in topic 2 right now. We're in the first week of topic 2. We're going to talk about a few other things in topic 2. But we're going to come back and we are going to like spend 2 weeks on this in March. Okay. Because this is kind of a big deal, guys, kind of a big deal. All right. So what we spent most of yesterday talking about were the root functions. And technically this was an Algebra 2 topic that we should have spent a lot of time in Algebra 2 talking about this, because, you know, linear and quadratic functions should have been covered very thoroughly in Algebra 1. And I'm going to reinforce that should have. Okay. So in Algebra 2, we're all going to pretend that we did spend a lot of time talking about the root functions, which are the inverse of our other power functions. And we can talk about the fact that for even roots, our domain and our range are restricted. Okay. So we have like basically 2 versions. We have evens, where domain and range are both basically greater than or equal to 0. And then we have odd functions, all right, where our domain and range are all real numbers. So this for values of p, okay, basically for f of x, where x to the p, where p is between 0 and 1, we have very, very distinctly two classifications, because we have what happens for an even root and we have what happens for an odd root. They all, in most general, they are going to have 1, 0, 1 y-intercept. Every function is going to have, with the exception of rationals, is going to have 1 y-intercept, because that's the way functions work. Odd ones are definitely going to have zeros. They might have more than one. I'm not 100% sure. But they are going to have zeros. They're going to start at zeros. It is also a possibility that they could be shifted up or left, up or down. That's a thing that could happen. In general, the behavior is going to be increasing, okay? Concave down in positive directions, concave up in negative directions. But in general, it's going to be increasing to the right and decreasing to the left. Now that could change if K is negative, but that's like the only exception. And then in general, we do have, once again, positive end behavior. It's a lot slower and less dramatic than some of the other power functions, but we are generally going to have increasing end behavior or decreasing end behavior if it's going in the other direction. Okay, now the second half of this lesson, which I'm actually like, because this was such like a boom dump of information, I'm going to hold off and save until tomorrow. So what we're going to end on is the whole idea of, regardless of how complicated a function is, okay, if it is the same power, it is generally going to have the same end behavior. So this function right here on the left hand, well, actually the red function, I should say, the red function is x cubed, hold on. The red function is f of x equals x cubed plus x squared minus 3. Okay, so the red function is super complicated. And as you guys can see, there's definitely a relative min and relative maximum. We've got big curvature changes, very dramatic when we're looking at the Zoom version. The blue function, on the other hand, is just x cubed. Okay, just x cubed, it's just hanging out there. I mean, and in the zoomed in version, there is a very dramatic difference. But when we looked at the zoomed out version, the functions look almost identical. And this is the result of looking at this end behavior, okay? The end behavior in both cases, okay, is more or less the same, okay? And that's kind of the takeaway we're getting to. The point I'm eventually getting to is that we can generally use simplified versions of functions to predict overall behavior. So even though a function at first could look really, really complicated, when we're trying to predict the overall behavior of the function, we can actually make it just a simplified version of it to predict some of these more zoomed out behaviors. And that is what we're going to pick up with tomorrow. I have an interaction in Desmos that is pre-written, and we're going to work through this tomorrow. We're going to pick up here tomorrow, and we're going to do some comparisons, and we're going to make some predictions based on simplified versions of the functions, and we're going to go from there. So that's about it. I did end about 10 minutes early.